Hello and welcome to the webcast entitled High Performance Medium Density Polyethylene Pipe Significantly Improves Abrasion Resistance in Industrial Mining, Energy, and Liner Applications. My name is Karen. I will be your operator for today's call. We have just a few announcements before we begin. At this time, all participants are in a listen-only mode. At the end of the presentation, we will conduct a question and answer session. The slides will advance automatically throughout the presentation. You can submit a question at any time using the Q&A box located in the lower right-hand corner of your screen. At the bottom of your console, you will find a help icon for technical assistance. If your screen freezes or the slides do not appear to be advancing as they should, please try exiting and restarting the session as it may be an issue with your connectivity. Please note that this conference is being recorded. Now I would like to introduce our two presenters. Wes Long is a Technical Projects Director for Performance Pipe, a division of Chevron Phillips Chemical Company, LP. Wes has a Bachelor of Science in Mechanical Engineering from Florida State University, with over 27 years of experience in polyethylene pipe sales, marketing, manufacturing, and technical support. Wes is an expert in applications for plastic piping systems and global resin supplies. Ashish Sukadia is the Global Polyethylene Applications Manager for Chevron Phillips Chemical Company, LP. Ashish holds a Bachelor of Engineering degree in Chemical Engineering from India, an MS in Chemical Engineering from the University of Louisville, and a PhD in Chemical Engineering from Virginia Tech. Since 2009, Ashish and his team have been responsible for new materials and applications developments, as well as global technical service functions relating to blown and cast film, extrusion coating, pipe, blow molding, rotational molding, sheet, and geomembrane applications. Ashish holds over 35 U.S. patents and has authored and co-authored over 60 conferences, journal publications to date, and is very active in the Society of Plastic Engineers and 10 conferences. I will now turn the call over to Wes Long. Wes, you may begin.
Good afternoon, and thank you for the introduction. I also want to thank all of our audience for taking the time to view our webinar today. We are very excited to introduce our latest new product, Driscoplex 4800 series. Our 4800 series is a brand new, high-performance, medium-density black polyethylene pipe that is designed to significantly improve abrasion resistance in industrial, mining, energy, and liner applications. Today, we will provide an overview of our new product, followed by an introduction of all the benefits and attributes of medium-density pipe, along with a discussion of the long, great history and tremendously positive track record of MDPE pipe. We will then cover the fundamentals of plastic abrasion or wear, followed by a discussion of pipe resin density and its effect on a pipe's wear rate. We will then cover the effect of a resin's molecular physical cross-links on plastic pipes' abrasion or wear resistance. Finally, we will review the recent third-party testing that was conducted and the data that was recorded. We will conclude with a summary of these results, followed by a question and answer session. Also, this webinar is being recorded and will be placed on our website for future viewings by those that were unable to attend today. Now let's review the standards and applications for this new product. 4800 series is a PE 2708 resin material, and the pipe is normally produced to ASTM F714 or D3035. For energy or oil and gas gathering and transmission pipeline applications, 4800 series can also be produced to API 15LE or ASTM D2513 upon request. The applications for this product are many and include mining, oil and gas gathering, produced water, liners, power plants, dredging, pumping, dewatering, bypass and drainage, sludge handling, wastewater, and stormwater. PE pipe has always been a frequent choice for transporting slurry solutions since it has been shown to have superior wear resistance to many different materials, including wear resistance 3 to 5 times greater than steel pipes. So basically, any application that benefits from enhanced abrasion resistance, particularly applications that may contain some type of slurry flow, should consider Driscoplex 4800 series. One of our products for mining applications has been our 1700 series PE 4710 pipe, which has one color, dual stripes or two stripes for DR identification. Many mining companies have always liked to have the ability to easily distinguish a pipe's DR, so years ago we established a color code for the various pipe DRs as shown on this slide. The double stripes, as opposed to a single stripe, made it easy for mines to tell which pipes were produced from PE 4710 material versus the old PE 3408 material. With the new 4800 series, we will utilize the one-color single stripe for DR identification, which will also allow for this pipe to be distinguished as a PE 2708 material. You will see in a few minutes that the new PE 2708 material has the exact same pressure ratings as the old PE 3408 material. This slide shows the history of advancement of PE resin materials over the years. These materials are recognized in ASTM with a material designation code that quickly identifies the most significant engineering properties of a PE pipe material. The code first identifies the material with the letters PE for polyethylene, and the first digit represents the density range of the base PE resin. This reflects the polymer's crystallinity, which in turn gives the material strength and stiffness. The second digit identifies slow crack growth resistance based on pent testing or Pennsylvania notch testing. And third, the last two digits provide the material's maximum recommended hydrostatic design stress for water at 73 degrees Fahrenheit. The PE 2708 material has the last two digits 08, which represents a hydrostatic design stress of 800 psi at 73 degrees Fahrenheit. This is the same hydrostatic design stress as a PE 3408 material, so the pressure ratings are the same. For resistance to slow crack growth, a PE 4710 material requires greater than 500 hours of pent testing compared to the previous PE 3608 material requiring only 100 hours of pent testing, while the new PE 2708 material achieves greater than 3,000 hours of pent testing. This virtually eliminates slow crack growth as a failure mode. Like standard PE 4710 materials, the PE 2708 is a solid wall pipe produced by conventional extrusion. The process is OD and wall thickness controlled to produce sizes from half-inch to 54-inch outside diameter with dimension ratios or DRs ranging from DR7 to DR41. In addition to the pipe's hydrostatic design stress we discussed, the pipe's specified dimension ratio or DR is used to determine the pipe's pressure rating or design pressure. Very simply, this is the outside diameter, OD, divided by the pipe's minimum wall thickness. So for a given outside diameter, the lower the DR, the greater the wall thickness. The wall thickness capability for this new product is generally limited to around 2 1/4 inches as far as the wall thickness. However, that is dependent on the diameter of the pipe. Basically, smaller diameter heavy wall pipes have more heat in the pipe than a larger diameter pipe. The bigger pipes have more surface area than smaller pipes, so the heat dissipates faster, resulting in less slump. So we can do heavier walls in bigger pipes than we can in smaller pipes. So please check with your distributor or pricing coordinator to determine the manufacturing capabilities to meet your requirements. PE 2708 pipe and fittings are pressure rated up to 140 degrees Fahrenheit, with the DR11 having a pressure rating of 160 psi at 73 degrees Fahrenheit and 100 psi at 140 degrees Fahrenheit. These next two slides show the long, successful history of medium-density pipe in the United States. When the first medium-density pipe was introduced in the early 1970s as a PE 2306 material, it had a 600 psi hydrostatic design stress. In the early 80s, PE 2406 material was introduced with increased slow crack growth performance. In 2005, PE 2708 material was introduced with an even greater slow crack growth requirement based on pent testing. The material also achieved an increased hydrostatic design stress of 800 psi by meeting the criteria for a high-performance PE material. Black medium-density pipe was first introduced in the early 1970s for potable water applications. Then, orange medium-density pipe was produced for natural gas piping beginning in 1974. By 1990, the orange medium-density gas distribution pipe was converted to yellow medium-density pipe. Yellow became recognized as the standard color for gas distribution piping in North America. Today, PE pipe represents over 98% of the pipe installed for natural gas distribution in diameters up to 12-inch in the U.S. and Canada, with the large majority being medium-density polyethylene pipe compared to high-density. Driscoplex 4800 series MDPE pipe was introduced in 2016 to provide superior slurry flow abrasion resistance compared to other polyethylene pipes. This is our 4800 series specification sheet, which can be found on our website, along with our model specification for 4800 series. The model specification provides a lot of valuable information, including information on joining as well as installation. For the next couple of slides, I will review some of the many benefits of our new medium-density 4800 series pipe systems. The key performance attributes of the new 4800 series pipe are that we now have black PE 2708 MDPE pipe and tubing listed in PPI's TR4 that meets or exceeds the requirements of ASTM F714, D3035, API 15LE, or ASTM D2513. As you will see from Ashish's slides that are coming up, the pipe has greater than 30% resistance to abrasion compared to HDPE PE 4710 pipe, providing longer service life in slurry applications. We also see this as a potential for customers to be able to use a thinner wall with a PE 2708 pipe while maintaining an equivalent life, resulting in significant cost savings in slurry applications. The pipe is also greater than 6 times more resistant to slow crack growth compared to PE 4710 requirements. Another significant advantage is this pipe has lower stiffness, which aids in field handling, bending, and installation. The 4800 series pipe also is greater than 2% lower weight per linear foot of pipe than HDPE PE 4710 pipe and tubing, so over 2% less weight per foot, and has greater than 2% carbon black protection, providing long-term protection against UV exposure. The pipe can be fused using the same fusion parameters as PE 4710 pipes and fittings, and I must say the MDPE makes a beautiful double rollback fusion bead, making it one of the easiest pipes to fuse and visually inspect for a quality fusion. The pipe is also produced with one color, single stripe for DR identification, or in solid black if preferred. And we also have the ability to supply a full range of pipe sizes, pressure capabilities, along with molded and fabricated fittings. Now I would like to turn over the presentation to Dr. Ashish Sukhadia to cover the fundamentals of plastic abrasion, followed by a discussion of pipe resin density and its effect on a pipe's wear rate. He will then cover the effect of a resin's molecular physical cross-links on plastic pipes' abrasion resistance, followed by a review of the recent third-party testing that was conducted and a summary of those results. Ashish, I'll turn it over to you now.
Okay. Thanks, Wes, and good afternoon to everyone once again. So the intent of the few topics that I will be talking about is really to give everybody hopefully an appreciation of some of the science and fundamentals that we looked at as we came to the design and solution of the resin that Wes has just talked about. I'll begin here with this general topic of abrasion, but it's interesting to note that the study of abrasion falls within a rather broad field of science and engineering known as tribology. Tribology has its etymology roots in the Greek word tribos, which means to rub or rub down or wear away. And thus tribology, in its most general sense or definition, is the study of, or perhaps more appropriately, the science and engineering of the behaviors and responses of interacting surfaces in relative motion to one another. There are then three main subfields or areas of science that fall within this broad field of tribology, and they are friction, which relates to the resistance to relative motion between two bodies or surfaces; wear, which relates to the progressive loss of material from the operating surface of a body occurring as a result of relative motion at its surface; and then lastly, lubrication, which relates to the use of a fluid, or in some cases even a solid, to minimize both friction and wear. So it is then hopefully easy to see how these three fields of science are so closely related, and perhaps the basis for why they involve common scientific principles. Our focus today, however, will primarily be on abrasion or wear. So abrasion, I should mention, is a very complex area, and the resistance of plastics to abrasion is dependent on many factors: the nature of the plastic, surface roughness, lubricating agents, load, material hardness, and beyond that, many other factors. The relative type of motion could be reciprocating, continuous, or geometrical in terms of sliding or rolling motion, operating conditions such as speed and temperature, the nature of the abrading material, size, geometry, concentration. And so perhaps the most important takeaway that I would like to leave you all with is the fact that the abrasion resistance should not be regarded as a material property, but rather a tribological system response, meaning that it depends on a lot of other factors and particulars of the system at issue. Abrasion resistance, however, could be broken down into two main classes, the so-called adhesive wear and the cohesive wear. In adhesive wear, which is also sometimes referred to as interfacial wear, that involves the transfer of polymer to a harder counter surface and its eventual removal as debris. Perhaps the most common day-to-day example is simply the process of writing with a graphite pencil on paper. Cohesive wear, on the other hand, involves either fatigue wear, which is failure due to a repeated dynamic loading, such as what might be seen in ball bearings as an example, or abrasive wear, which is essentially a cutting, plowing type of damage due to a permanent plastic deformation. And a couple of common examples here would be the wear on kitchen knives or currency coins after many, many years of use. So now wear is generally thought to be basically proportional to the applied load and inversely proportional to the hardness, meaning that a harder material might be expected to wear less. Now, while that is generally true in the case of metals, it turns out that in the case of plastics, that's actually not true. Contrary to popular belief and intuitive belief, it turns out that the abrasion resistance of plastics do not correlate directly with hardness or proportionately with hardness. In fact, most of the data in the literature has actually found just the opposite. I show a little snippet here that hopefully you all can see. It comes from this referenced article by Lowe and Marshall, and I'll take a quick minute just to read that. It says metals tend to have greater abrasion resistance as their hardness is increased, but polymeric materials have shown a trend almost opposite to this. German work with data from different locations showed a trend of increasing abrasion resistance of polymers with decreasing elastic modulus. The opposite trend was observed for metals and materials with elastic modulus of around 10 giganewton per meter square, which were found to be less abrasion resistant under direct impact abrasion conditions. The point basically then is that the difference is thought to be due to the fact that in metals, which are much harder, as the hardness increases, it's more difficult to form a scratch or a gouge. But then once a scratch or a gouge has formed, it's easier to remove the material. Plastics, on the other hand, are much softer, and although they may scratch more easily, the material removal is harder due to the elastic nature of the material. In other words, the viscoelastic nature of polymers affects the abrasion resistance characteristics more so than simply hardness, as is the case with metals. So we look now at a little bit of data from the literature to support this notion that abrasion wear in plastics is really quite different from that in metals. We begin by looking at some data from the reference article again by Lowe and Marshall, where these three different plots are shown. The left one here is wear rate as a function of tensile yield strength, wear rate as a function of tensile modulus, and then the wear rate as a function of the tensile yield strength. And what we basically notice here is that each of these properties, the tensile yield strength, the tensile modulus, or the tensile yield strain, they are all basically directly dependent on the density. And if you take the sort of composite analysis of what these three charts are telling us, all three results suggest consistently that the wear rate is higher or worse with higher density. In this slide here, we show some data from an article by Lancaster, which was published in the Wear magazine in 1969, so it's a fairly dated article, but the science has actually remained much the same. This plot basically shows the wear rate as an inverse of the ultimate break strength and the elongation product, which is shown on the x-axis here. And plots like this have been subsequently shown in the literature many times and are referred to as the Ratner-Lancaster Correlation. Basically, the x-axis here, the product of the tensile strength at break and the elongation is an indication of material toughness. Therefore, as toughness increases, this product increases. But note here that this axis is the reciprocal of that product, meaning that tougher materials are to the left side here, and they generally show less wear. Now, for polymers, many molecular factors will come into the picture, but other things being equal, generally lower density resins are tougher and therefore will exhibit lower wear per the results of this study as well. We then move on to look at yet another set of data that was published in the Macromolecules magazine in 2002, an article by Terwood. And this was a fairly seminal study and perhaps most relevant to the work here because they investigated the abrasive wear behavior of linear polyethylene resins of a very broad range in terms of their molecular characteristics, spanning basically 3 orders of magnitude in molecular weight, different distributions, both monomodal and bimodal, and then a variety of polydispersities or molecular weight distributions ranging from monodispersed, meaning around 2, all the way to as high as 80. And their goal from this work was to elucidate the macromolecular origin of abrasive wear in polyethylene. And perhaps what was the seminal part of their finding was the fact that they found that the abrasive wear for plastics was primarily dependent on what they referred to as the effective number of physical crosslinks per macromolecular chain. We look here at a couple of key results from that published study, and shown here in this slide are basically 2 of their plots. The left one here is the wear coefficient or the wear rate as a function of this parameter phi mn star, and then the right one here is the wear coefficient or wear rate as a function of crystallinity. So the left chart basically shows that the wear rate decreases as this phi mn star product increases, and this product is basically a reflection of the number of physical crosslinks. So in other words, as the number of physical crosslinks increases, the wear rate decreases. On the right side now we see, and keep in mind again this was all data for polyethylenes only, and therefore more directly relevant, crystallinity is directly tied to density, and you can see very clearly here then that this data shows that as the density increases, the wear rate also increases in a fairly linear fashion, meaning once again that the lower density products would be expected to have better wear performance. So we basically took all of this science and understanding and decided to do a little bit of testing with our own resins to see if these fundamentals held true. To that end, we basically took 3 different polyethylene resins within the Chevron Phillips pipe family, the medium density resin that Wes talked about a little while ago, a unimodal high density resin, which was a PE 4710 class pipe grade material, and a bimodal high density PE 4710 class pipe material as well. And this was done really to give us a good broad range of molecular structures and therefore make the results in that regard more relevant. The tests were conducted at White Rock Engineering Services based in Texas. And in the results that you are going to see in the next couple of slides, bear in mind, please, that a lower SAR or slurry abrasion response number indicates better abrasion resistance. And then to cover the effects of temperature, we did the test at both room temperature, 73 degrees Fahrenheit, and the elevated temperature of 140 degrees Fahrenheit. Just a little bit about the details of the ASTM test by which these tests were conducted, ASTM G75. That standard basically is a standard test method for determination of slurry abrasivity, which then allows one to determine a Miller number or the slurry abrasion response of materials, in which case the results are represented as an SAR or SAR number. This test method can determine either the relative abrasivity of any slurry or the response of different materials to the abrasivity of different slurries. And so there's some flexibility in terms of how the test is conducted. The slurry abrasion response number, or the SAR number, is a relative rate of volume loss of any solid wearing specimen in a given slurry. And in our particular case, which is a fairly standard test protocol for this test, the test was conducted using AFS 50-70 test sand, and basically 150 grams of sand, 150 grams of deionized water, meaning that the concentration was 50% by weight of the abrasive media, which was in this case, again, sand. We start and look first at this table here where we have listed the resin properties, primarily the high load melt index and the density. So again, the unimodal and the 2 high density resins. And shown in the lowest row there, what we refer to as the abrasion index, is using the same methodology and principles of the published paper that I talked about earlier. And in going through the analysis, it showed that the medium density resin would have a higher abrasion index, meaning a better resistance to abrasion than either of the 2 high density resins. So this gave us a little more confidence in terms of the approach we were taking. And then the key was really, do the experimental data that we received from the lab actually support that? And that's shown in this slide here, where what is actually shown on the left axis is the SAR, or the slurry abrasion response number. And the data is shown, the first two columns are for the medium density, and the two bars, the lighter bar, the gray bar, is for the 70 degrees F, 73 degrees F, and the darker blue bar is the same data for the 140 degrees F. So two temperatures. And you can see clearly that, as I mentioned earlier, the lower the SAR number, the better the abrasion resistance. And you can see quite clearly that there's a noticeable difference of about 35% lower abrasion for the medium density relative to either of the two high density materials. This was basically further validated by simply looking not at the calculated SAR number, but the raw mass loss at the end of the 6 hours of the test. So this is a cumulative weight loss, and that data is shown in the lowest two rows at the 70 degrees and the 140 degrees F temperatures. And basically you can see quite clearly in the raw data itself that we see a fairly significant difference in terms of the high-density resins, both of them showing much higher wear on a relative basis compared to the medium-density resin. One last slide on this, where we took the data that was published in the article that I referenced by Terwood et al. That's the data in blue. And then Chevron Phillips had data for a number of different polyethylene resins that we had tested over time using the slurry abrasion response test, the ASTM G75, and that data on the left slide is superimposed with a shifted factor just to accommodate the data all on one slide in red. And then that Chevron Phillips data is shown on the right just by itself, and you can see the very same trends that we saw earlier, which is that the slurry abrasion response number is an exponentially dependent factor in terms of this physical crosslinks. So this basically validates our thinking and further validates the fact that the medium density pipe with the higher physical number of crosslinks should have, as the data then supported, significantly improved abrasion resistance. So to summarize our findings and looking at the same abrasion data in a little different way, this is now looking at essentially thickness loss, which in terms of a pipe conveyance system may be a more relevant or directly relevant way to look at it. And again, of course, as expected, the data shows the same trend. The medium density pipe is better in terms of abrasion resistance compared to either of the two high densities by a factor somewhere around 30-35%. And this is data at 73 degrees Fahrenheit. And then the same type of data for the 140 degrees Fahrenheit test shows the same general trend with a range of anywhere from 30 to 40% improvement relative to the two high-density resins. So in summary, I think we feel pretty good about the data that we have generated, which appears to show, as much of the literature that I covered showed, that the abrasion resistance of plastics seems to be pretty well defined through the concept of this effective number of physical crosslinks per macromolecule, and as originally proposed by Terwood and his group. It's a little counterintuitive, but it's interesting to note that the abrasion resistance of plastics does in fact show an inverse dependence on hardness or crystallinity, and the wear is influenced by the elastic nature of the plastic. As predicted from the fundamentals, the medium density resin indeed was predicted to show better abrasion performance or higher abrasion resistance compared to the two high density resins, and the data in fact proved that out quite well. And so thus it is our expectation that this particular unimodal medium density 2708 pipe resin that Wes talked about is going to perform very well in mining, industrial, energy, and liner applications, and is clearly indicated based on data to be a better choice than either bimodal medium density or unimodal bimodal high density resins or pipes due to the better abrasion resistance that we are seeing and is rooted in the fundamentals of the polymeric response. So with that, Wes, thanks to the audience for listening, and I'll turn it back to you.
All right, thank you very much, Ashish. We hope you will consider our new Driscoplex 4800 series MDPE pipe and fittings for the many benefits we have reviewed today. The new pipe material is perfect for most applications, and particularly those requiring a flexible but tough, lightweight pipe with increased abrasion resistance. Thank you again for joining our webinar. We'll now take a few minutes to answer questions that have been submitted, and I'm going to turn this over to Connor Bush to go through the questions that we've seen come through so far.
So one question we got was about how particle size in the slurry affects the polyethylene pipe. And in general, there's a couple of generalities that go along with the particle size and the hardness. So if the larger the particle size, typically the more wear we see on the pipe. And that's true up until about a particle size of around 100 microns, and after that, the effect becomes negligible. Same goes with hardness. The harder the particle, then the more the increase in the rate of wear on the polyethylene. Another one is like the shape of the material for the particles. The more rounded it is, the less wear it creates on the pipe, while the more sharp angular solids can gouge the material more and create more wear. And then lastly, increasing the concentration of the solids increases the rate of material loss, but that's also only true up until about a 20 weight percent. After that, the interface is saturated, and increasing the solids concentration in the slurry has a negligible effect as well. Yeah. Oh, and one more thing is the ratio. While if the particle size increases or the slurry becomes more abrasive, while it will increase the wear on the pipes, that will happen across all the types of pipes. So the ratio between how the 4800 medium density pipe performs compared to the high density pipes would be the same. One other question we had was about the whether or not the ASTM D2513 traceability will apply. So once the PHMSA approves the new plastics rule, the ASTM 2513 track and traceability will apply if required for application. So the ASTM 2513 won't be the standard, but if it's requested, the 4800 can be made to meet those requirements.
Any other questions?
Let's see.
Wes, I see one question with respect to...
tensile yield. Can you answer that?
Right, the relative tensile yield. So I can try to answer that. I guess the first thing there is that the tensile yield strengths for polyethylene are very well correlated with density. In other words, they are essentially a reflection of the density. To the specific question, the tensile yield elongation, which I assume is maybe what is being asked. I'm not sure if the question was yield elongation or strength, but the elongation is roughly around 10-11% tensile yield for the 2708 material, and about 14-15%, so slightly higher as expected. And the other way around, 10% for the 4710 and about 15% for the 2708 material.
Very good. We have another question here. Is the PE 2708 material cheaper in general than the PE 4710? It'd be best to refer that to our commercial group, although I will say that with the density being less, the weight per pounds per foot is less. So for a given price per pound, the price per foot would be less with the medium density compared to the high density material. But I'll refer the pricing question to our commercial team, which your pricing coordinator or your distributor would be able to better answer that question. Let's see. Do we have some other questions?
There is one, and I hopefully didn't write down something in error. The question is, can you clarify the first bullet on the summary slide? Does increasing the number of crosslinks increase the wear resistance or decrease the wear resistance? So increasing the number of crosslinks, physical crosslinks, is expected to and does increase the wear resistance. In other words, the wear resistance improves or absolute wear is lower.
Yeah, I think that's clear. Very good, Ashish. Let's see, what's this other question? Ashish, do you want to address this? A question about does the increase of flexibility of MDPE material for fittings, would it lead to more wear due to vibrations in piping? I would.
Due to vibrations, I guess I don't know that I have a first-hand knowledge of that to answer that, but just in terms of vibrations, given the fact that the medium density would have more of a damping effect, I would expect the vibration effect to be worse for the high density than for the medium density.
Yeah, I would agree with that. Let's see, have we answered? Which plants? Okay, we have a question here. Which plants will this material be extruded? Currently, we are extruding this pipe in Brownwood, Texas, StarTex, Knoxville, and Reno. Pryor has made the pipe before, but probably not Pryor due to their focus on gas piping. But really, almost all of our pipe plants can make this product, really no limitation there. Any new questions? I think Ashish, unless we get a new one here. Okay. I don't see any new questions.
There are a couple new. I think people are typing them.
Got a couple new ones here. Where will fittings? Our fittings are produced in Bloomfield, Iowa, for our molded fittings. And would you recommend this PE 2708 over PE 3408 in general? Oh, absolutely, for abrasion resistance. And quite frankly, the PE 3408 was replaced with PE 4710 back years ago. And it was actually quite astonishing. But one of the things that led us to this study was when we converted to the higher density 4710 materials, we actually received several complaints from mining customers or customers that were used to using our pipe in abrasive applications that they noticed that the 4710 material did not have the wear resistance or abrasion resistance of the previous 3408 material. So given the study and the theory that Ashish has presented, we now know that they were right. The 3408 actually performed better than the 4710 because it was a lower density material. But now with the 2708, we developed it knowing that, or thinking that it would be even better than the previous 3408, which we've tested and confirmed.
There's one question that's just come in, Wes, and I can try to take a stab at it. The question says, is it fair to say that customers using 47 today for slurries, that they will get 30% more life than they are currently getting? And Wes, you can chime in or correct me. I'll just give my thoughts. Lifetime predictions for all kinds of systems are always difficult, so I don't know that I would be able to say that we would get 30% more life. But I think based on the fundamentals covered today, the data we have generated and shared, it's probably a fair statement that the 2708 will give a longer lifetime than the 4710, and the abrasion data that we presented would appear to indicate that it's not a small effect. It's, if you consider 25-30% range, a substantial effect.
Yeah, absolutely. I would agree with you, Ashish. It's going to give a substantially a longer service life, but it's hard for us to predict exact service life because of the different applications.
There's another question, Wes, relating to, says in general for slurry transportation, the PE 4710 was always recommended for velocities less than 3 meters per second. Said this, can we use PE 2708, can be used for larger velocities? I know abrasion depends on many things. And I think that's exactly right, is that the abrasion is dependent on many things, as you just stated and as we mentioned earlier. I would say, though, that in terms of the effect of just velocity, it's been well established, it's well known that the higher the velocities, the higher the abrasion capacity of the abrading material. But in terms of the relative response of the 2708 to 4710, I am not aware of anything that would suggest that the 2708 shouldn't continue to outperform at the higher velocities. That would be my response.
So one thing to keep in mind when dealing with slurry flow is you want to try to maintain a velocity that keeps you in turbulent flow. If you're in laminar flow, your slurry particles will settle at the bottom of the pipe and just constantly slide along the bottom of the pipe surface and wear it down. If it's in turbulent flow, the particles will suspend in the liquid and it'll reduce the amount of contact between the pipe and the particles. There's an equation called the Duran's equation that gives a critical velocity, and you'd want to maintain a velocity at least above that critical velocity. In general, good practice would be to keep a flow velocity at 30% above that critical velocity, so you wouldn't risk going below that. So while it is true that a higher velocity, it'd obviously be hitting the pipe at a higher speed and causing more wear, if you keep a turbulent flow, then you'd be just less contact in general and less wear overall.
All right, it looks like we have a final question here. Can we get PDF copies of the presentation for discussion with engineers and customers? The taped presentation somewhat hampers the discussion. Absolutely. We will make the presentation available in PDF and can send to those upon request. So just send your request to Wes Long here, and I will email you a copy of the presentation. But again, it will be on the website for some time, and it'll have the full recorded version available for later viewing. And with no other questions, it looks like we can conclude. One other thing I wanted to point out, that we have a brand new technical note. I meant to put this in the presentation, but we just published a brand new technical note called PP844, entitled Slurry Abrasion Resistance in Polyethylene Pipe, and it outlines the results of our third-party test data, along with some of the information provided in the presentation today, and it's available on our website under Engineering Information, under Industrial. Go to your Industrial tab under performancepipe.com, and you will hit the engineering information tab, and at the bottom we list all of our technical notes, and I think next to the last technical note is the new one for slurry abrasion resistance in polyethylene pipe, an outstanding technical note that gives all of the summary of the report and data we received from the third-party engineering firm. So please access that and share that with your customers as well. So with that, Ashish, I think we've covered everything. Do you have anything to add?
No, Wes, I think you got it. I was just scrolling to see if there was any other unanswered questions, but I think we are good, yeah.
Well, very good. Again, I'd like to thank everyone for taking their time out of their day to listen to our webinar, and we really appreciate your interest. For the distributors, we appreciate your business, and for engineers and customers out there, we greatly appreciate everything and your interest in the product. So thank you, and this concludes the webinar for today.
Thanks, everyone.
Thank you, ladies and gentlemen. This concludes today's conference. Thank you for participating. You may now disconnect. Speakers, please stand by for your post-conference.